Hello everybody! Do you know the problem? You have prepared some wonderful barbecue food, you have invited over your family or friends, and now the barbecue doesn't work because the barbecue gas bottle is empty. This is super annoying and it also can get really embarrassing. I've always wondered what the best solution for this problem would be. Of course, you could buy a spare gas bottle, but actually I'm not a big fan of having a spare gas bottle lying around in my house unused. Also, this doesn't help you if the gas bottle gets empty right in between your barbecue action. This is even worse because then you have everything already grilling and then suddenly the fire stops. Super annoying. So I wanted to find a solution that notifies me when the gas bottle is about to get empty. And it should be a smart solution which integrates well with my smart home solution of choice, Home Assistant. This would also allow me to create some additional automations based off the state of the gas bottle. In this tutorial, we will build a DIY gas bottle level meter which integrates with Home Assistant. Enough talking, let's jump right in.
Smart home maker, rock the beat. Innovation at your feet. Build it up, don't complicate. Home solutions, you're the mate.
Let me explain the basic idea behind the planned solution. The gas bottle sits in a compartment below the barbecue gas grill. My idea is to install a battery-powered smart scale in this compartment in order to weigh the gas bottle to identify whether it's full or empty. Okay, so what do we need for this project? First of all, we need an ESP8266 powered D1 Mini. Then we need 4 half-bridge load cells and also an HX711 PCB. This is a little PCB that usually comes already with the load cells and it is used for reading them out and transforming the value to something that you can read out with the D1 Mini. Furthermore, we need a DC-DC step-up converter to convert the voltage from the batteries up to 5 volts for the D1 Mini. Then we also need 3 1.5 volts AA alkaline batteries. We need an electrical switch. We need a 200 or 220 ohms resistor. We also need some wires and we need a 3D printer and some filament. Here you can see the wiring diagram. The wiring is a little more complex, so I would propose that you just pause the video or you can just go and visit my blog because I will also create a blog entry about this. The blog can be found under the-smart-home-maker.com. First of all, we have to wire the 4 load cells. You can see in the picture how to wire them. The white connections in the picture correspond to the white wires coming from the load cells. The kind of grayish connections on the picture correspond to the black cables coming out of the load cells, and the different reddish connections come or correspond to the red cables coming from the load cells. Then you connect them as shown in the picture to the HX711 and you connect the HX711 as also shown on the picture to the D1 Mini. This allows us to read out the load cells and get the gas bottle weight. The second thing we need is of course some power source, and for that we use the 3 1.5 volts alkaline batteries. We connect them in series so that they add up to 3 times 1.5 volt equals 4.5 volts. Then we feed these 4.5 volts to the DC-DC step-up converter, and from there we go to the 5 volts input voltage of the D1 Mini. And we have to, of course, make sure that the DC-DC step-up converter is configured in a way that it outputs 5 volts. For the model you see in this picture, it's quite easy. They have some small resistors, and depending on how you set those small resistors, you can just adjust the voltage. And for this model, exact model here, we just have to unsolder all of those two resistors to make sure that it will add up to 5 volts power. One further thing I have introduced here is an electrical switch, so that we can easily turn on or off the solution. And I have also added a wire that goes to the analog input of the D1 Mini, and we use this in order to measure the voltage of the batteries, and by this identify whether the batteries are still full or already empty, because I think this is very important to know. Otherwise you have this device sitting outside in your garden, in your barbecue grill, and you never know when the batteries are empty. Next step is to design the housing for the gas bottle scale. I started with the top part, which is just a round lid which has a hole where we can attach it to the bottom part, and we have some little areas that can push down the load cells in order to measure the weight of the gas bottle. And now let's have a look at the bottom part. This is the bottom part. Looks like this. Here you can see. With this part here, I can kind of attach it to the top part, but the top part is still kind of moving up and down so that it can push down the load cells. Here we can place the 4 load cells, which will be pushed down by the top part in order to measure the weight. Then we can turn it a little bit to see what's here. We have the space for the D1 Mini ESP8266. We also have a space for the batteries. We have a space for the boost converter. And we have a space for the HX711, which connects to the different load cells. Okay, now let's push those parts to the printer. Okay, printing just for the bottom part took me about 18 hours. And then I tested it and I realized that some of the holes were not big enough and were not high enough so that I could really put the wiring in, and then I had to redesign and print again, and then I realized that I had forgotten something else and I had to redesign and print again. So this process took a very long time because the printing just took so long. And the same thing for the top part. The top part took also about 15 hours to print. So overall, printing the bottom and the top part already took some days, and then I had to repeat the process because I adjusted the files and printed again. So it took a little while to get this figured out, but now I have a version that's okay from my point of view for a first prototype and allows me to test the solution. This is the very first prototype of the solution. You can see that the batteries power the system, we have a switch to turn on or off the solution, and we have the D1 Mini, which is the brain controlling everything. This is how the final prototype looks like. You can see I added some insulation tape to kind of push the wires down, and you can also see that the 3D model is still not perfect because the wires do not fit perfectly, but it's okay for now. And you can also put the lid on in order to measure the weight of the gas bottle. Now that we have built our prototype, it's time to create the ESPHome YAML file and also to calibrate the load cells, because the load cells need to be calibrated in the final setup in the housing that we've built. And so we needed to wait until the prototype was finished before we can work on the ESPHome YAML code. We will now have a look into the ESPHome YAML code for the gas bottle scale. First of all, of course, we define some basic stuff. I think this is nothing special. What's interesting here is this on-boot script. This is something I will explain a little later on. Then we have the ESP8266 board. We enable logging, we enable the Home Assistant API. This is very important so that we can get data also from Home Assistant. We allow over-the-air updates, of course. We set the Wi-Fi credentials. We set a fallback hotspot in case Wi-Fi connection fails. And then, now comes the interesting part, we have our sensors. First of all, we have the platform HX711. This is the little HX711 board which connects to the load sensors and gets you the value for your weight. So I give it an ID, I give it a name, then I say the data out pin is on GPIO 0, the clock pin is on GPIO 2. You saw that in the wiring instructions. Then we have some gain that we can set, but for the situation I just leave it with 128. Then I set an update interval of 1 second, which is quite often. Maybe I will also change that in the future. Then the interesting part is the calibration. This is something we will see once we have flashed this to the device, because the load sensor will kind of dump out some values, and then you can identify which value is 0, which value is 1, for example, and you can define unit of measurement, and in my case this is kilogram. So actually this is 0 kilograms, this is 1 kilogram, for example. And you can do that by, for example, just leaving the scale as it is, and then read out the 0 value, and then you just put something on the scale which has 1 kilogram or 5 kilograms or whatever, and then just get the value that the load cell outputs and put it here. Okay, the next thing I have is the platform ADC. This is the analog to digital converter, and here I want to read the battery charging value. So the battery actually is the battery voltage. So this is being read on pin A0, and here I want to also have a quick update interval. I could also lower this for the future probably, but for now I've set it to 5 seconds. So then I also calculate the battery charging state in percent, because this is of course much better readable and also easier to use in automations. Here the unit of measurements is percent, and I have a lambda function that calculates this, and I can explain this a little further when we see it in the wiring diagram I will show you in a second. Then we have also the gas bottle fill state. So for this I have identified that the gas bottle probably has about 8 kilograms once it is completely full, but I have to actually check this once more. And then I say, okay, if it's 8 kilograms, then it's 100%. But this value might also change once I have further information about the weight of the gas bottle. Okay, then I have one more thing, and this is now very important. I want to put this device into the deep sleep mode. This means that the ESP8266 will go into a special sleeping mode where it requires only a lot less energy than when it's running normally, because when it's running normally it requires all the Wi-Fi connection, and this takes up a lot of energy, and in this sleep mode it just sleeps and just uses enough energy to be able to wake up again in a certain time period. So it just counts the time and then wakes up at a certain point of time, and then it consumes more energy again. But this is very good if you operate on battery, and our gas bottle scale should work on battery, and that's why we need to minimize the energy used. For now I have defined that the battery scale will just run always for 1 minute, and then it will go to deep sleep for 60 minutes, or we could also say 59 minutes, so that it overall every hour it wakes up and then sends out a value and then goes to sleep again. But to be honest, in the future I might even lower this further, because it might be absolutely sufficient to read out the value once or twice a day, because you don't grill all day and use up the gas bottle all day, or at least I don't, because I have to work also, etc. So it is also possible to set it to maybe once a day, and then the rest of the time the system could be in deep sleep and consume much less energy. But one problem with the deep sleep: if you have only 1 minute of run duration, how should you enable OTA updates? This is not possible, because in this 1 minute you will probably not be able to kind of hit the right point, because when you want to make an update, you have to compile the update, and then at some point when it's compiled, it starts to flash it, but it has to be made sure that the ESPHome device is online at that point in time and not in sleep mode. So this is very difficult, and that's why I wanted to integrate some kind of possibility to set the device into an OTA mode. And this is quite handy. So I have included the script here. I found it in the ESPHome community forums. It's really cool, because this script, what does it do? It first of all, it logs that it's checking the OTA mode now. Then it checks whether the binary sensor OTA mode is on. And what is this binary sensor? It's this one here. It is a sensor that's imported from Home Assistant, a binary sensor. So the cool thing is here, I can set this binary sensor from within Home Assistant and say, okay, this is on. So that means the devices should go into OTA mode. And in this mode, if it's on, then OTA mode on, lock OTA mode on, and prevent the deep sleep. This is really great. So in this OTA mode, the device will not go into deep sleep until the next checking step, and this will be done after 2 seconds. There's a delay, and then it will execute test OTA again, so it will go to this script, through the script again. So you can always switch the OTA mode on or off, and if it's on, the device will prevent the deep sleep. So then you have enough time with the device being online for flashing the firmware update, and once you finish the firmware update, you can just put the OTA mode to off, and then the device goes to deep sleep again. And I think this is really helpful and cool. And then of course I have the Wi-Fi info, the IP address that I want to send out to Home Assistant. That's it. So now we have a little excursion here. I wanted to explain to you how I calculated the battery percentage, and this is the explanation now. On the left side of the screen you can see two resistors, R1 and R2. R1 has 220 kilo ohms and R2 has 100 kilo ohm. And this is a so-called voltage divider. You can see there is a pin A0. This is the actual analog input pin on the D1 Mini. And we have another pin, this is the ADC of the ESP8266. This is the connection that goes to the actual ADC input of the ESP8266. And the reason for this voltage divider is that the ADC of the ESP8266 cannot cope with more than 1 volts of voltage. And that means that we need to kind of scale it down. But on the A0 input, you can put in up to 3.3 volts, because this is the normal voltage in the ESP8266 environment. And that's why they added already this inbuilt voltage divider on the D1 Mini board. So this makes sure that when there is a voltage of 3.3 volt, it is actually only 1 volt that goes to the ADC of the ESP8266. And if the A0 voltage is below 3.3 volt, it goes down respectively on the ADC of the ESP8266. But for measuring the battery voltage of my 3 alkaline batteries, we have more than 3.3 volts. So the batteries, they have nominal 1.5 volt, but if they are completely new and fully charged, they can go up to 1.63 volt, as far as I read in the documentations. And that means that if you have 3 of those, they can add up to 4.89 volts. And we need to make sure that this will not blow the ADC of the ESP8266. That's why we add this additional resistor R1 with the accent. This is the violet resistor. And if you have 2 resistors in series, then they can just be added together. And so the voltage divider can be scaled down further. And this is something we can calculate here. So the battery voltage can go from 4.89 volts when they are completely full down to what I read. Usually they are kind of considered empty when they have only 1.3 volts. So then they go down to 3.9 volts. And we need to make sure that we can measure 4.89 volts at 100% and 3.9 volts as 0% battery voltage or battery charging state. So this is what we do, and we can calculate this with a voltage divider. The normal equation for the voltage divider is U1 divided by U2 equals, and then we have R1 plus R1 with the accent, so those two added together, divided by R2. And if I calculate this with this formula, then I get an R1 value of 169 kilo ohms. Actually, I don't have such a resistor at home, so I only have a 220 kilo ohm resistor. And with that I have to kind of recalibrate the whole calculation. So I can then calculate which U2, this is the actual voltage that goes to the ADC of the ESP8266, which U2 maximum and U2 minimum values we can get. And this is calculated by those formulas you can see here. And if I calculate this, I can get 0.92 volts on the ADC of the ESP8266 when the batteries are fully charged, and 0.66 volts if they are empty. And with this I can now calculate the battery percentage, because I can take the value that I read on the ADC of the ESP8266, this is U2. I just subtract the 0.66 volt because this is the absolute zero line. So if this division U2 minus 0.66 volt equals 0, then we have 0%. And if this equals 0.92 minus 0.66, we have 100%. And that's why I kind of divide it by the difference between U2 max and U2 min, which is 0.26 volts. And that means in the end we have U2 minus 0.66 volts and then divided by 0.26 volts and then multiplied by 100% gives us the battery percentage. So this is now the logging output from ESPHome. And here you can see different information. You can see, for example, our gas bottle weight. It's here. It says got value 81822, for example, and then 81808, 81770. So you can see it's a little bit drifting. So this could be a problem when I'm continuing with this project, but for now this is how it is. And we can use this value to calibrate. So we could, for example, say around 81800, it's a 0, because at the moment there is no weight on the scale. Now we can scroll down and we can see that if I now put some pressure onto the scale, you see the value goes down to 747 something, 75, 78, depending on how much pressure I put. So you can see the scale is working. No, I released it again and we are back at around 800 or 700 something. Yeah, so you can see it's not super accurate at the moment, but I mean, for this application I don't need super high accuracy, right? I just need to be informed when the gas bottle weight is very low or very high. And I mean, such a gas bottle usually has about 5 kilograms of gas. So there's definitely a difference whether I have 5 kilograms or like 1 kilogram. And I think this accuracy here should be sufficient for that application. This is how it looks like if I put the scale into the cutout for the gas bottle. So now I put the gas bottle on top of the scale and I will turn on the device. And here you can see how everything shows up in Home Assistant. You can see the battery charging analog digital converter value and also the battery charging state, which is 53% at the moment. And you can also see the gas bottle filled state in percent as well as the gas bottle weight. So the weight is about 3 kilograms and it's also drifting a little bit. I think the 3 kilograms is too low, of course. This is definitely a calibration issue, so I have to adjust the calibration. And I might also have to have a look at how the drift is maybe being improved, because you can see it is drifting a little bit and this is not good. I mean, I don't need a super accuracy because it is just that I want to know, is it filled or is it empty? I don't need all the states in between, but still it should be kind of accurate, because if it's just drifting so much that I can't even detect properly whether it's empty, then of course it wouldn't help me. But I think, as you can see, it is kind of only drifting around the 40%. So this looks okay from my point of view. I just think the absolute value is too low because the gas bottle isn't that empty at the moment. But this is something I can adjust. Well, now you saw a lot in this project, I think, and this is already a very long video. So there are some open points. I would need to properly calibrate the load cells in order to get a super accurate value for the gas bottle weight. And also, of course, I would have to set up the automations afterwards in Home Assistant, but this is super easy, right? So you just need to set up an automation with a trigger value for the gas bottle percentage, and then you just say, for example, if it is below 30 or 20%, you want to get a notification, and then you send a notification to your smartphones and computers via Home Assistant. And you can also use your favorite voice assistant to send a voice notification out so that everybody is informed that the gas bottle is empty and needs to be replaced. Furthermore, of course, I would also add an automation for the battery so that I get notified if the battery percentage is below a certain threshold, because of course, if the battery is empty, the whole system will not work anymore. So this is also important to be able to replace the batteries once they are empty. Okay, so this was it for today. I hope you really liked this video. If you do so, then also please hit the subscribe button, hit the like button, so to let me know that you like it and also be informed about my upcoming videos. And if you have any comments, remarks, further ideas, please leave a comment below. Thanks a lot and see you next time.